All right, let us keep going with oscillations. We are working towards being able to understand waves, which will be important to analyze in terms of sound, in terms of water waves, in terms of a lot of things that can be described by a wave phenomenon. All right, so to recap, we were looking at the idea of something that undergoes repetitive motion. The pendulum of a clock. If I wait, if I look at this, it does the same thing over and over and over again. And without friction would do so indefinitely. A ball attached to a spring, undergoes repetitive motion. The Earth going around the sun is some sort of repetitive motion. In that case, it's 3D repetitive motion. Versus, more 1D or 2D motion like springs and pendulums. And we saw that, and we were looking at an example of, suppose you had a box on a vertical spring, so gravity was pulling down, the spring force was restoring and pulling up. There was some equilibrium location where the box was completely stationary, the forces were in balance. We can find that location. We could have found that location back in chapter 5. But then if I were to pull the spring down a little, or pull the box down a little bit so the spring was more stretched, there is more of a pull from the spring than there is from gravity, and so as a result, the box shot back up. But then the spring became compressed or less stretched when it got above that equilibrium position. In that case, gravity started to win, and then gravity pulled back down, and the thing oscillated up and down as a result. And we made some crude estimations of what the position, velocity, and acceleration looked like. And we saw that even in the case of something that takes data at finer points in time, like in the case of this spray paint oscillator, where the spray paint bottle is attached to a spring, so it will oscillate up and down. But then the spray bottle is constantly shooting paint, which allows us to record the vertical position of it as a function of time. That is what the cardboard is able to do, I guess whatever this kind of paper this is. In which case you can see the repetitive motion looks very sinusoidal. And that is where we will pick up from in analyzing this motion a little bit more and trying to relate it to physics. So we define a kind of motion. There's many kinds of motion that can be repetitive, but might not look like nice sinusoidal sorts of motion. And so we can define a motion, call it simple harmonic motion. And we can call it simple harmonic motion when it takes a particular form. In this case, in the case of the vertical height of the spray can or the mass on the spring, we can say that simple harmonic motion is motion that oscillates back and forth, up and down, what have you, in such a way that it can be described by a sine or a cosine function. And as I've written it down, this is the most general way to write oscillating motion, but I've introduced 3 unknown variables here. This A, this omega, and this phi. And then time marches forward, and we get something that might look like oscillating motion. But the idea is that now we need to understand kind of what these represent. What each of these represent, and then how do we tie them into physics. So A is called the amplitude. It is a measure of the height of the wave, or in this case of the oscillating motion. So if I go to my little diagram here, in 1 second, let me augment it real quick. I want the amplitude to also be an option. And I need to tweak this. I think that should be enough. Yes. All right, let me move that onto the screen. Wave motion is really nice because it can be described very easily, and mathematical expressions can be helpful here. I made it too big. So the idea here is, essentially I have this plot. What it's going to plot is it's going to plot this function as a function of time. So the horizontal axis is time. The vertical axis could be y of t in this case. And I want to see how it depends on various parameters. The amplitude is just giving you a sense of the height of the wave, or the height of the oscillation. In terms of thinking of it as the mass that's bobbing up and down, you could think of it as the maximum distance it is away from equilibrium. So in this case, the amplitude is 0. This is a straight line. But as I increase the amplitude of the wave, what happens is that the height increases and increases. I can give you the number as well. So the amplitude of the wave is telling you how high are the peaks, how low are the troughs. The height that goes from the midpoint to the top, so in this case from 0 to something like 1 1/4, I guess 1.27 exactly, let's just make it 1 1/4. That is the amplitude of the wave. What is the height of the wave? What is the lowest, what is the distance from the middle to the bottom? Or what is the distance from the middle to the top? That's the amplitude of the wave. Whether the wave is small or big. Or whether the oscillation goes, just bobs up and down in a small distance, or does it really, go all over the place? Should not lean on the keyboard. Phi here is we call it the phase angle. The phase angle, really all it's saying is it's telling you what is going on at t equals 0. You can think of it as just a shift. It shifts the wave left or right, depending on the value of phi. Let's look at it again. So in this case now I have phi here, which I'm going to keep the amplitude, as it is, so we can see how phi changes things. So right now phi is 0, and if I increase phi slowly, the only thing that happens is that the entire wave just shifts a little bit. So what is going on at t equals 0? In this case, at t equals 0, it looks like it's starting going a little bit down before it turns around and comes back up. For a different phase, this is for a different phase that says when I plug in t equals 0, what's going on is it's starting to go down, but it's starting at a height, that's about, 0.7 or so above, the equilibrium point, the 0 point. In this case, with no phase, it started at its maximum height, which in this case was 0.755. That's my amplitude. Let me change it just 3/4. So all this is doing, it's shifting to tell you kind of what is going on at t equals 0. Usually, the only reason you need a phase angle is just to match, say, your initial conditions. If you know that you're starting with a box on a spring, and you're starting with the box, perhaps it starts moving and it's at some intermediate point of its maximum position distances that it can obtain. You can quantify that by just saying that there starts with some sort of phase angle. We won't see that terribly often. Then there is omega, which we used to call the angular velocity. In the case of oscillating motion, we call it the angular frequency. Oh, I guess I should also go back and talk about the units of these things. So the units of A, if you're talking about actual motion, right, this might have units of length. For example, phi itself is an angle, so it has units of radians. And omega is an angular frequency, and like angular velocity, it has units of radians per second, say, or angle per time. Everything you know about angular velocity also applies to what we are now calling angular frequency. We just call it a frequency because it's the frequency that we'll see that what it plays a role with is that it adjusts the frequency that the oscillations are occurring at. Is the oscillation going very quickly, or is it taking a very long time to go up and down? For a vertical box, say. So it is saying something, says how fast oscillations occur. And again, very similarly, it relates to the period of oscillations. How long does it take before the thing starts to repeat itself? If the box starts at the top, goes down, then comes back up, how long does it take to go from the very top and then come back to the very top? Or how long does it take to go from the very bottom, come up, go back down, get back to the very bottom? This period is still just defined as 2 pi divided by omega, as we've defined it before. Since you will sometimes see it talked about in terms of frequency, let's remember we don't want to confuse angular frequency with frequency. Which frequency, thinking back to chapter 4, I think it was, we had defined as just 1 over the period. The period says how long it takes to complete one oscillation, 2 seconds. The frequency is saying how many full periods occur every second. So if the period was 2 seconds, the frequency would be 1/2 per second. It completes half of a full oscillation every second. And recall that the frequency has units of hertz. 1 over seconds has units of hertz, where period obviously is units of time. So MKS units has seconds, for example. Just to remind ourselves of what are the relationships between these variables. Some of these which we've seen before. So in this case, I need to actually move this forward with time. So in this case, I'm going to keep the phase at 0. I'm going to keep the amplitude at 0.75. And then I'm going to set omega, the angular frequency, now as 1 radian per second. And what I'm going to do is I'm going to let time just march forward, and this is going to be shown as an animation. Let's slow it down a little. So if I let time just march forward, you can see that it looks like there's some sort of oscillation that occurring. It kind of looks like the oscillation is moving to the right. But we got to be a little careful here because remember the horizontal axis is time. It's saying that at a given point in time, here is what the object is doing. So I think really it's better in these sorts of situations for oscillations. Just look at the vertical axis and look at where the black dot is drawn as the animation moves forward. And you can see that the dot along the vertical axis is bobbing up and down. So you can think of this as the box on the spring at the very top, then it's charging down, slowing down, coming to rest, then starts to move back up, etc. And if I were to adjust omega from 1 and upgrade it to 2, you might notice that what's happened is that the oscillation is occurring faster. It's bobbing up and down much faster, and I could speed it up even more. So now it's almost, let's just go all the way to 3. Here the oscillation is occurring even more rapid. As it's bobbing up and down, if you look at the vertical axis, it's bobbing up and down much faster than compared to when the angular velocity was something like 1 here. And if I adjust it smaller, so now it's 0.3. As time marches forward at a steady clip, the frequency of oscillation is occurring. The frequency is much smaller. the period is much longer. It takes longer for, if it starts at the top. Oh dear, what has happened? It takes longer. I'm not sure what's happening here. Someone has hacked me. There we go. For example, when the omega was really high, right? I could calculate the amount of time in between the points where it's at its highest or where it's at its lowest, for example. That time would be shorter, smaller period, compared to when omega is much smaller, like in this case, it's about a half. If omega goes all the way down to 0, then even though time is marching forward, you can't really see it anymore, but there's the time bar. It's always marching forward, but nothing's moving. There's no angular frequency. There's no oscillation that's occurring. So if the bob starts, at 0.75, it remains at 0.75. If there was a phase, so that it started at, say, negative 0.3, it would stay at negative 0.3 as time goes forward. But now we can think about what happens, and then what does it mean for omega to go negative. So here omega is 0.11, so it's moving very slowly to the right, kind of looks like. A negative omega just means that it's oscillating in the opposite direction. So for oscillating motion, there's really no difference between the two. It goes up, comes down, it goes up, and repeats itself. But this will be important when we start talking about waves. When we get into wave motion, where we're thinking about what is the wave doing both in time and in space. Like a water wave goes up and down, but it might be moving, across the ocean. In this case, the value of omega, whether it's positive or negative, will have some meaning. In a sense, it will be a vector quantity of sorts, like what we've seen in the past with omega and how it plays a role. All right, stop this. I'll move this off the screen. All right. So that's kind of mathematically the idea of simple harmonic motion. But we would like to understand the physics of how all of these quantities are determined, or how they are set based on the problem at hand. If we go to the idea of a massive box on a spring, I could think in terms of forces, we are now very comfortable at writing down that gravity pulls the box down, but the spring pulls the box up with some force of negative kx, for example. I guess in this case, kx pointing upward if the spring is compressed, or stretched rather. And their magnitudes might be the same at some points, or in the case of a bobbing box, they aren't always in perfect equilibrium, and so the box continues to accelerate and move. Right? We looked and saw that acceleration also appears to be kind of sinusoidal in a sense, and we'll see that there is a mathematical connection between the position, velocity, and acceleration in terms of sines and cosines. Actually, we could just write that down. No, let's not. Let's do the experiment first. So I tried to do this on my own, and it just did not look as good as what I could find that colleagues have done elsewhere with big production teams versus me alone in the lab. So I think what we're going to do is we're essentially going to look at this experiment of a vertical box that's going to bob up and down. And the question is that we want to see, we're going to focus on, say, just the period. If I want to understand oscillating motion, one quantity that's usually of interest is how long does it take for it to start repeating itself? And we could ask, does the period depend on the amplitude? Does the period depend on the spring constant? Or does the period depend on the mass? You think the first one, the amplitude, is based on how much you displace the box before you get it going. You might think if I have a larger amplitude, that means more distance has to be traveled before the object starts repeating itself. But if you have a larger amplitude, that means you've stretched the spring more to get it started, so there's a greater force as well. Similarly, just how does the spring constant affect the period? If I do the same experiment, same amplitude, same masses, but I double the spring constant for one spring compared to the other, does that change the period? Because then the spring is stronger, it's stiffer. And then similarly, if I hang, an apple versus if I myself hang onto the spring, what sorts of does that change the motion? Which that relates in a sense to the gravitational force that's pulling down. Let's see. All right, so the idea is that we're going to conduct these three experiments. So that's set up, but we're going to look at different amplitudes and see how that changes the period. We're going to look at different spring constants and see how that changes the period. Then we're going to look at different masses and see how that changes the period. And with that intuition, with that experiment, we're then going to try to mathematically show this relationship. The relationship where that is suggested.
We're suspending the mass from the spring, and the other end of the spring is attached to a fixed, rigid object. The period of the motion is the time required for one oscillation. Boom, boom, boom. So it's the time between booms.
All right, so the idea is that this first experiment, I cut some of the video out on the explanations. So the first part of this experiment is they're going to just keep the same spring, keep the same mass, change the amplitude.
First the amplitude, and in order to just get a rough idea about how the period depends on amplitude, then let me look at a couple of different amplitudes. Here's a fairly small amplitude, boom, 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 boom. Here's a medium amplitude, boom, 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 boom. And here's a large one, boom, 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 boom. And back to the small one again, and we're just getting a rough measurement here. Boom, boom, boom. I think you can tell that the amplitude, or that the period doesn't seem to be depending much, if at all, on the amplitude. And in fact, the mathematics bears this out.
So in that case, by measuring booms, in all of those cases, even though they were quite different amplitudes, the period was essentially the same in all of those cases. There seems to be a very weak, if at all, dependence on the amplitude, and as he's hinted, actually it doesn't depend on the amplitude at all. Even with the larger amplitudes where more distance is being covered, there is a larger restoring force from the spring, which provides a larger acceleration, so it covers that more distance in the same amount of time. Next idea is now we're going to keep the amplitude the same, keep the spring the same, but change the mass.
You can remember how fast the last one is going. First thing to notice is that our equilibrium position is no longer at 19 centimeters. It's down at around 36 centimeters. And then if I give it some motion and look at the period is now boom, 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 boom. It's slower, takes longer. And then bringing this to the extreme, even longer period, equilibrium position much lower. Boom, 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 boom. Very, very long period motion.
So in that case, what we found, by increasing the mass, same springs, same amplitudes. Well, actually, it doesn't even matter, really. I didn't even really need to say same amplitude, because we showed in the previous experiment that the amplitude doesn't impact the period. So I could have used, you could have done very different amplitudes in all of the cases and wouldn't have mattered, since amplitude does not impact the answer. which is why he likely was which is essentially what he was doing. He wasn't being very careful at what the amplitude was when he got them started. But what he did find is that the larger the mass, the longer it took for motion to start repeating itself, or we say that the period increased. You should also think about what it means. The equilibrium position got bigger, the spring was stretched farther. That's a good review of chapter 5 of why that would have been the case. So now finally it's going to be, we keep the mass the same. Again, the amplitude doesn't really matter. And then we're going to change the spring constant.
If I use 2 springs instead of 1, I thereby doubled the spring constant. So let's compare the period with just one spring and this large mass. Boom, 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 boom. And the same mass with 2 springs. You know first that the equilibrium position is higher because we got more force pulling it up to counteract gravity. Boom, boom, boom. A little bit faster period. So, a shorter period, that is.
All right. Enough of the booms. So what was the takeaway here? What did we realize by doing these experiments is that by looking at the period, and of course we could have been more precise, used actual clocks and stopwatches and whatnot. What we would have found is that the period does not seem to depend on the amplitude, which says that the angular frequency does not depend on the amplitude. Remember, period is related to angular frequency by the period is 2 pi divided by omega. So by measuring the period, we are saying something about the angular frequency. But it did seem to depend on the spring constant and the mass. With the stronger spring or larger spring constant, there's a stronger restoring force. You get more force for a little bit of displacement. And as a result, the object oscillated faster, or the period was shorter. The period going down means the angular frequency should go up. The rate at which it completes, 2 pi radians increases. And then we saw the opposite for the mass, that as the mass increased, it took longer for the oscillation to start repeating itself. We could view that as the period goes up. Remember, period is the time for repetition. That gets larger. Which means that the angular frequency gets smaller as a result. So now we could try to argue how and why, what is going on here. In this case, what we're going to do is argue via dimensional analysis. And then we can show that this is the case for a more simple relationship. We had a couple quantities in the problem. We had the amplitude, we had k, and we had m. You might think we also have little g, which is playing a role of gravity, though the mass really is kind of connected to gravity in this case. The amplitude was shown not to matter. And in this case, we were using the same, little g wasn't changing at all. So just to remind ourselves, k, the units of k, this was the spring constant, which was newtons per meter. The units of mass were kilogram. Then the units of g was meters per second squared. I could ask myself, if I want to measure the period, it seemed to be that it depended on K and M, particularly. Maybe it also depends on G, but it seemed in this case to depend on K and M. So I could ask myself, if I'm going to come up with some formula, a formula that might depend on K, M, and G, I know that units don't lie. So I know whatever combination of variables I use in my expression for the period, it must have units of seconds. Else, this is nonsense, and this entire semester has been a waste of time. So I could ask myself just dimensionally, how can I combine K, M, and maybe even G to get something that has units of seconds? For example, I could say, okay, what if I do K times M? Well, the units of K times M is Newton per meter times kilogram. That is not units of time. That is not units of seconds, for example. I could instead ask, what about, say, M divided by K? And that actually might make sense, because we saw that when we increased the mass, it took longer for the oscillations to occur. The period went up. So it kind of makes sense that maybe the mass should be in the numerator. And then when we increased the strength of the spring constant, the period got smaller. It took less time for repetition. So that makes sense that maybe K should be in the denominator. So then if I look at the units, this is kilograms divided by Newton per meter, or kilogram meter per Newton. Or Newton is itself kilogram meter per second squared. Indeed, it seems like the kilograms cancel, the meters cancel, and what you're left with has units of seconds squared, which is not units of seconds, but it's really, really close. So with that, you might say, okay, what if I say instead the square root of M over K? That has units, then, of the square root of seconds squared, or has units of seconds. And it turns out this is the only way to combine these so that that is the case. For these three particular variables. So what this shows, without me doing any fancy calculus or derivations, this suggests that whatever this function of period is, it is at least proportional to M divided by K, the square root of M divided by K. This doesn't tell me exactly how they're related to one another, but it tells me how they must depend on the things that have units. So I could say that the period is proportional to the root M over K. Proportional meaning, this is equivalent to saying that the period is some constant multiplied by square root of M over K. The constant is some dimensionless number, 3, pi, 6, -1, that doesn't have units, and it's multiplied by whatever the thing that has the units, which must have units of seconds, because this is a period. We will see that the answer, the true answer, which requires the full derivation, is that constant is 2 pi. So we will see that this is, the answer is the full complete answer is that the period is 2 pi times the square root of M divided by K. But at least in trying to reason out the proportionality, how the period must depend on these parameters, we could have done this first before doing the experiment. And then the experiment would have justified this sort of scaling, and that increase the mass, increase the period, increase the spring constant, decrease the period. All right. Now let's actually try to show this and prove where this comes from. So, simple harmonic motion math. let us start with our definition, where we said simple harmonic motion is defined by this. That is the most general form of simple harmonic motion. The derivative, or the velocity, can easily be calculated. You are likely masters at doing this sort of derivative at this point, and we are far enough in the semester because I have to use the chain rule, but we're far enough that I'm pretty sure we've all seen the chain rule as well. So then this just becomes minus a sine of omega t plus phi. Then by an application of the chain rule, an omega pops out. So then I would write this as a negative a omega sine of omega t plus phi. This a times omega has units of meters per second, because a was meters. Omega was per second, radians per second technically, but radians is one of those weird units you can ignore. So a omega, has units of meters per second. Sometimes this is called the maximum oscillation velocity. The oscillation, it moves. Sometimes it's going very fast. Sometimes it's, it comes to a halt at the very top and the very bottom, and then it turns around. You could ask, what is the range of velocities? It goes between 0 and some maximum number. This V max is kind of the maximum amplitude of the velocity. Let's see, going back to this, right? While none of this is to scale, they don't necessarily all have to be the same height. In the case of the velocity, it oscillated up and down, and there was some maximum height and minimum trough location for the velocity. So there's some max location that is given kind of algebraically as the amplitude of the oscillation times omega. The acceleration, which is just the derivative of velocity, is just another application of the derivative, which in this case becomes minus a, another omega pops out by the chain rule, and it returns back to a cosine. By a little algebra rearranging, I could rearrange this so that I put a particular choice of items in these brackets. And if I stare at that long enough, you might notice that what I have there in brackets is nothing more than the function for the position of the oscillator. So I could write this instead as minus omega squared y of t. This is technically the definition of simple harmonic motion. Simple harmonic motion is motion such that the second derivative of position is minus omega squared times the position. Or said another way, that the acceleration as a function of time equals minus omega squared the position as a function of time. These are equivalent statements. And this, mathematically, actually is how you define simple harmonic motion. Simple harmonic motion is motion that obeys these relationships, where the acceleration of the object is equal to minus some number, which in this case we're quantifying as the square of the angular frequency, times the position of the oscillator as it oscillates back and forth. Or that the second derivative of position, the acceleration, is minus omega squared times position. You see this a lot. Whenever you see, for those of you continuing on in physics and engineering, whenever you see acceleration equals minus a number times position, if you see a equals minus 3x or something like that, where a, of course, is the second derivative of x in this case, in this context. Whenever you see that acceleration is equal to negative a number position, you immediately No, you immediately know that this is simple harmonic motion. It can be nothing else. Simple harmonic motion is defined by this. When you take a differential equations class, you would actually prove this in the opposite direction. You would start with this expression here. This expression is called a differential equation. It's an algebraic equation that involves not only y, but also the derivatives of y. Differential equations, it's essentially algebra, but when you're solving for x, but solving for x might also require you to know about the derivative of x, or the second derivative of x in this case. So whenever you see an expression like this, where acceleration is some minus a number times position, that is the definition. You know immediately that that is simple harmonic motion. And you can use the expression on the right to immediately also identify what the angular frequency is going to be. It's whatever that number is out front. It is that is equal to the square of the angular frequency. Let's do an example to show that, so that I don't have to deal with weird equilibrium positions. Let's do the box on a spring, but I'm going to do it horizontally on a frictionless surface. You could do this for the vertical spring. You would get the same answer. We've considered the forces of a box on a spring, attached to a spring that can move kind of back and forth when we did Newton's laws. We can now look at it again in the context of simple harmonic motion. We could not solve this with Newton's laws. The expressions were too hard. Ultimately, what you would have been doing is you would have been solving the equation for simple harmonic motion. So I had to just posit the answer. Here, essentially, I gave you the answer and we showed where it came from, so you could do this proof in reverse. But let's suppose now I take the box, I move it out to the right a little bit and let go. The box will then start oscillating back and forth. The spring will pull it in until it gets squished, and then it will be pushed back out, and then it will oscillate back and forth. The spring will alternate between squished and stretched. A free body diagram of the mass would show that the sum of the forces on the box, which must equal the mass of the box times the acceleration of the box, is just minus kx, how much it's stretched or compressed, and that equals the mass times the acceleration. Or I could rearrange this to say that the acceleration is minus, in this case, k over m times the position x. And now I say, compare this with this. I said simple harmonic motion is when you can write the acceleration equals negative a number times position. What I've highlighted in green here is saying that the acceleration is negative some number times the position. So by making a comparison between this and a equals minus omega squared x, you can identify that omega squared, what is playing the role of omega squared here? You're saying that omega squared equals k over m. I have to go to a new screen. So a equals minus k over m x, and we're saying compare that to a equals minus omega squared x, which is right, this is what we mean by simple harmonic motion. This is what we got from Newton's laws for a horizontal spring. This suggests that omega squared equals k over m, or this suggests that omega is root k over m. I can immediately say what the angular frequency is based on the physics of the problem. I can also then immediately say what the period is, because if I know the angular frequency, I know by definition that this is true, that the period is 2 pi divided by omega, which then becomes 2 pi m over k in the square root. Again, notice the relationship that we derived just by looking at the units is still there. The period goes as the square root of m over k, which matches the experiment that was shown in the video. The actual math allowed us to get the true equation that there was this 2 pi out front, where by just looking at the units, we could only say something about how it scales with m and k. And notice not the amplitude. The amplitude doesn't appear at all in this expression. The math borne that out, and that was also the saw that in the experiment. You could, of course, ask, surely the amplitude means something, right? There's some meaning to the amplitude. And you saw that in the video, that when the amplitude was large, it was covering a lot more distance, and at points it did seem to be moving much faster as it was trying to cover, because it had to cover that same distance, or sorry, it had to cover more distance in the same amount of time. The period was the same, whether it was doing this or whether it was doing this. The period was the same. But in order to cover the more distance in the same amount of time, the average velocity must have been faster. If the average velocity was faster, then you might think that that says something about the total energy of the system. Conveniently, springs are conservative forces. So we can also write down something about what is the total energy of the system. And we know that this energy is conserved. So that no matter where the box is, as it's bouncing up and down on the spring, the energy is always the same no matter where the box is, whether it's at the top, whether it's at the bottom, whether it's whizzing through the middle. The total energy must be conserved. Let's actually write down what that is. So total energy T is the kinetic energy plus the potential energy. Let's stick with the horizontal spring so I don't have to worry, Again, the gravity term ultimately cancels itself out if you were to do this as a vertical spring. And you get the same answer. But it's easier to derive for the horizontal. So for the horizontal, well, I guess for anything. For the kinetic energy, it's 1/2 mv squared. For the spring, recall that it was something like 1/2 kx squared. But we have expressions for what x and v are. We derived them on the previous slide or page. So we know what is the position and the velocity as a function of time. Sometimes it's moving, sometimes it's not, as the position bobs, in this case, left and right. And it's doing so with some amplitude, which we really haven't said anything about, but we know it does have some amplitude, and it might have some phase as well. Though again, that ultimately will not matter. And it's doing so at some angular frequency. So then, math away. 1/2 m v squared then is a squared omega squared sine squared of omega t plus phi plus 1/2 k x squared, so then that's a squared cosine squared of omega t plus phi. Oof. There are some common things there, like there's a 1/2 and an a, so maybe I'll pull those out. So this looks like it's a squared divided by 1/2. And then it looks like there's a m omega squared times sine squared of omega t plus phi. And then it looks like there's a k, I guess that's it, cosine squared of omega t plus phi. So if I were to plug in time, this would give me some function of what the energy is. But I just said that total energy was conserved, because you only have a conservative force acting on the box as it bobs, left and right in this case, or up and down if you were doing it vertically. So this does not, I should be able to convince myself that this is indeed a constant. This looks like it's going to be some weird function that changes. The connection to be made is, if we recall, we said up above that omega squared was k over m. So omega squared was k over m for this case. Or that m times omega squared is equal to k. That's convenient because we have m squared right here. So we would replace that with k. So then this becomes a squared over 2, and then both terms have a k in them, so I can factor that out. Then it looks like it's sine squared of omega t plus phi plus cosine squared of omega t plus phi. If you only remember one trig identity, the one to remember is the Pythagorean trig identity, where the sine squared of theta plus cosine squared of theta is unity. That entire thing in the brackets is unity. The total energy in this case, we just showed, is equal to 1/2 k times the amplitude squared, which is indeed a constant. K is a constant. A was related to the maximum displacement. This is the total energy. So as some of it goes into kinetic, some of it remains in potential, but it oscillates back and forth between the two. We could draw those, the bar charts like we've been doing, where kinetic and potential would just oscillate back and forth between kinetic and potential, of just, the spring being stretched and not stretched at all. And you should think about that. We will likely do this in the handouts, of just at what point in the oscillation is the object moving the fastest? What points are it at rest? When is position, velocity, acceleration all maximized and minimized for oscillations? They don't occur at the same spots. Mm-hmm. All right. Where am I at time? All right, good. Let me do a simple example. I think this is number 10 of the problems at the end of chapter 15. An oscillating box on a spring takes 0.75 seconds to begin repeating its motion. Find the period, the frequency, and the angular frequency. This is actually kind of simple. Should have done a better one. So it repeats every 0.75 seconds for a mass that's attached to a spring. That implies the period is 0.75 seconds. The period is defined as the time it takes to start repeating yourself. The frequency of motion is 1 over the period. So in this case, if the period is 3/4, then this is 4/3, or 1.33 hertz, or 1.33 per second. And then the angular frequency is 2 pi divided by t. So in this case, I could plug in all those numbers, and I get something like 8.37 radians per second. If I then said the mass of the box was 2 kilograms, I could then ask myself, what is the spring constant in this case? And if we scroll up, we can see that we wrote down that the relationship between, we said that omega was equal to root k divided by m. If we're interested in k, knowing omega and m, then this says that m omega squared equals k. This one I actually forgot to calculate in advance. So in this case, I guess it is just 2 kilograms times 8.37 squared. which gives me a spring constant of about 140.1 newtons per meter. Again, notice I said nothing about the amplitude. Nothing, repeats every 3/4 of a second. It doesn't matter what that displacement was. So this is kind of the basic idea behind simple harmonic motion. Really, if you want to claim that something is undergoing simple harmonic motion, you have to show, the goal is to show that it obeys these sorts of expressions, that's highlighted in blue here. If you can, through Newton's laws or some other expression, write down and show that the acceleration equals negative some number multiplied by position, you can immediately say, aha, this is simple harmonic motion, and then I can write down that as my answer for the position as a function of time. And then the amplitude and the phase are kind of just determined based on the exact problem you're doing, but you at least know from physics what omega is going to be. Omega will always depend on the properties of the system. The amplitude and the phase depend on exactly what your experiment is, how you've set up your experiment. For example, let's take the pendulum. Let's take a simple pendulum, right, where you have some mass attached to an essentially massless, rod or string. If I release it, if I give it some displacement, in this case an angular displacement, it bobs back and forth repetitively. If I were to take, a lot of snapshots of what's going on, it would suggest that it's undergoing something that looks like simple harmonic motion. So the idea here is, can we prove that and then see how things like the period, how long it takes for oscillations to start repeating themselves, how it depends on the properties of the system. So here is the setup. This is sometimes called the simple pendulum. The simple pendulum meaning that I'm going to have some length L here, but all the mass is going to be concentrated at this ball at the end, or this it's a point particle at the end. We'll do the physical pendulum, probably not today, but in the next lecture, where you can take into account the actual shape of the pendulum. Okay. In this case, clearly motion is occurring. It bobs back and forth. We could actually even do the experiment to see how things might depend. The mass is not changing, so I can't do that experiment. But I could keep the length short and kind of displace it and do this. Boom, 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 boom. I could then make the length longer. Boom, 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 boom. Seems like the period is getting longer. So I might expect the overall period to depend at some positive, power of the length of the string. And I can't control the mass, so we will have to leave that be. All right, so let's analyze the system. In this case, it oscillates. I might create some initial displacement that is some angle from the vertical. And then it oscillates back and forth by bobbing, it comes down, then sweeps back up. So it's going back and forth in terms of the angle. You can measure the angle from vertical, call that 0. And then it goes back and forth between positive and negative angles, about the vertical. And that occurs by gravity pulling down on the mass. So first I could ask myself, what are the physical properties of the system, the things that have units? I have the length, L, which has units of, say, meters. I have the mass of the rod, or the ball at the end of the rod, which has units of kilograms. And then I have G, which is meters per second squared. And I could ask, how does the period depend on these particular parameters? And you could do the same exercise and ask, how can I combine L, M, and G such that I ultimately get something that has units of seconds? I'll let you fill in the blanks. I'll just skip to the answer. But you can show that the square root of not K over M, but in this case, L over G. The square root of L over G has units of seconds, which again suggests that the period, the actual period, should be some number, I'll call it, beta, times L over G. We don't know what beta is yet. Just by looking at the units, we've only been able to argue through dimensional analysis that we expect the answer to be something like a number times the square root of L over G, which does match the one experiment I just did. I made the string longer, and it took longer for repetitions to occur. The period did seem to increase with a longer string. So the experiment is at least supporting the scaling initially. So now we could actually analyze the system in terms of a free body diagram. Gravity is pulling down on the bob, which causes it to move back and forth. If the bob is straight down, there's no real desire for it to rotate. Gravity pulls down. The moment arm about my axis of rotation is along the vertical as well. There's no torque in that case. Though if it's at an angle, the moment arm is along some distance, that's the string. Gravity is pulling straight down. There is a torque. There is a desire to make this thing start rotating because of a gravitational torque. So the gravity is torquing the ball as a result. Going back up to the drawing, if I call this my axis of rotation, then there is a moment arm that goes along the string, that is R, the moment arm, and then there is a force due to gravity, which points straight down. As a result, there is an angle between them, which, with a little bit of thought, you can see is the same angle, theta, that's drawn on the diagram. Okay. So there is a torque, which I could say is the moment arm cross F. In this case, the force due to gravity. The way it's drawn, that has a tendency to make it want to rotate clockwise. The cross product, my thumb points into the page, is going to want to make the thing rotate to the left. And then once it gets to the other side, the torque actually changes directions. And once it's swinging on the left side, if I do my moment arm cross, and then my fingers point towards F sub G, my thumb that goes from pointing into the page to out of the page. There's a tendency to make it want to rotate counterclockwise. And so then the oscillation starts to occur. If I look let's look just at this snapshot here. So if I look just at that snapshot, the magnitude of the torque in this case is going to be the magnitude of the moment arm, which is L, the magnitude of the gravitational force, which is mg, times the sine of the angle between them. And since, given the way I've made this drawing, there's a tendency for, at this point, it wants to rotate clockwise and not counterclockwise. Remember, we said clockwise is assumed to be the negative direction. And Newton's second law says that this torque equals then the mass of the object equals the rotational inertia of the object times the resulting angular acceleration. If I treat this as a point particle, the rotational inertia is just ml squared times some angular acceleration. in this case, I guess we could simplify things a little bit just to get us started. The m's cancel. That's nice. So it looks like now I can say, and then I guess one of the l's cancels, and then I can divide by the other one. So it looks like I can write something like minus, or I guess I can write alpha equals minus g over L times sine of theta is what I get from Newton's second law for rotation for the pendulum. This does not quite look like simple harmonic motion. Remember, we want to say acceleration equals minus a number times position, or the angular equivalent, angular acceleration equals minus a number times an angle. So this alone, a pendulum for any arbitrary initial angle, I get started out like this, and it swings, would not undergo simple harmonic motion. If I were to measure the period, something like this, or if I were to measure the position as a function of time, this would not this would not be a perfect cosine or a perfect sine angle or function. Though I would find, if I made the displacement very small and did something like this, the motion would look more and more like simple harmonic motion the smaller I made that angle. So we can look at pendulums. So when you look at a pendulum, like a grandfather clock, or like an actual pendulum clock, the big grandfather arm of the clock is not swinging 90 degrees to 90 degrees. It is moving a very small angle, usually less than about 10 degrees or so. So in those cases, it's nice to make an approximation to what's going on, or the small angle approximation, which is true more or less when theta, this is more or less true when theta is less than or equal to about 20 degrees. You might have shown this in Calc 1. You would also prove this in Calc 2 with Taylor series. You could also just convince yourself on a calculator. When theta is small, plug this into your calculator, sine of 2 degrees, you'll get essentially 2 degrees back. The sine of an angle is approximately just the same as the angle when when theta is very small. You might in Calc 1 have proved that the limit of sine of theta divided by theta as theta goes to 0 is equal to 1, which essentially says in that limit sine of theta equals theta. A way to interpret that is it's saying that when theta gets really, really small, sine of theta and theta are approximately the same thing. If you take the sine of an angle and it's tiny, you get essentially the same number back. Sine does not change anything. We call that the small angle approximation. It can be very helpful when you're dealing with things that are oscillating at very small angles. That's useful in this context because if I make the small angle approximation, then that says that the angular acceleration is equal to negative g over L times the angular position. So notice we have angular acceleration equals minus a number times, in this case, the angular position. This is indeed simple harmonic motion. For pendulums where the maximum displacement is not too big, angles that are less than, say, 10, 20 degrees, this motion is very well described by simple harmonic motion. Where we can then say that the angular frequency is equal to, the square of that is equal to g over L, or that the angular frequency is the root g over L, or that the period, which is 2 pi divided by omega, equals 2 pi, the square root of L over G. again, showing us, we convinced ourselves this should have been the scaling, the square root of L over G. And we're seeing that the math actually shows this to be the case, which is a treat. Right, so for pendulums, right, you might see, in your book and whatnot, that the pendulum, the angular, or rather for the simple pendulum, the angular frequency is given by G over L. The period is given by 2 pi L over G as a result. For the simple pendulum, where the rod essentially has 0 mass and all the mass is in the bob at the end. Which for physical pendulums isn't too bad, because usually, there's a lot of mass weighted at the end to make an actual true pendulum more or less a simple pendulum. That's usually why, for old style clocks, the pendulum does have that big ball at the end. So again, what is the takeaway here? The takeaway is for simple harmonic motion, if you want to study oscillations, physics determines things like the angular frequency. And we can determine what that is by looking at the expressions, usually via Newton's second law, and finding instances, if I can show that there is a connection between the position and the acceleration where they're related by it minus a number. The minus is key, because the minus is saying that this is the result of a restoring force. If I go past equilibrium, there's an acceleration that tries to pull me back towards equilibrium. Then if I overshoot, the force or the acceleration changes to point in the opposite direction to again try to bring me back to the center, back to equilibrium in this case. This is only true for restoring forces.